using transformations. Also, find x and y intercepts algebraically. Good. What is the base function used? Which base function did I use here to create this function? Did I use the absolute value? Did I use the square root? Did I use x squared? What did I use?
Used to the x.
That's it. That's what I used. Number 2, what will be the next transformation on 2 to the x?
The negatives instead of it.
Careful.
The plus one.
Good. What does it do when I change x into x plus 1? Where does the graph go? To the...
Does the graph move right?
Careful.
Left?
Yes. So left 1. Number 3, negative 2 to x plus 1. What will this transformation do to this one?
Reflected.
Very good. Thank you. Reflect with respect to the x-axis. Very good. And number 4?
It's gonna go up. So.
Thank you very much. Great job. Good. Let's graph all this. But first I would like to find the x and y intercepts. And then we'll graph all of them in a minute. How do I find the x-intercept for any function? I'm going to copy the function here because I'm moved on to the next page. How do I find the x-intercept for any function?
You find the zeros?
Yes. So the x-intercept means that I have to set y equal to 0, which is negative 2 raised to x plus 1 plus 4 equals 0. What type of equation is this? I'm looking for my first 2 pages that I always torture you with. I got them. I forgot to torture you with this today. Just kidding. See, you already know 8 types of equations. This is number 9, and this is coming up. So obviously, this is an exponential function. Equation, I meant to say. And you can say, we've never solved this before. True, we haven't. Let's give it a shot. Common sense. What would you do? You don't know anything about it. We have never seen this before. But we do have common sense. And you will tell me what you would do. What you would do for sure as the first step.
This is a case of substitution.
No. So we have the equation negative 2 raised to x plus 1 plus 4 equals 0. What do you think? It's okay if you're wrong. Say it again. I just talked at the same time. My apologies.
Subtract 4.
Of course. That's common sense, although we don't know anything about it. The next step is also common sense. What would you do?
Find a number to substitute with x.
Too many negatives. I don't care for negatives, right? We always clean it up, so let's clean it up. This looks much better. And I notice that the base here is 2. Is there any way I can write this side with the same base? With the base 2? Is there a way? If there isn't, I cannot use this method, and you will have to wait till the next section And I'll show you how we solve it, even if they don't have the same base. But is there a way of presenting 4 with the same base?
You do the second.
Excellent. Now, 2 numbers are equal and they have the same base. How can they be equal? Only if x plus 1 and 2 are if x plus 1 and 2 are what?
Equal.
Exactly. There is no other way. So then x must be 1. So we found the x-intercept as 1, 0. And you had no idea how to solve this. And now you do. Okay, now the y-intercept. How do I determine the y-intercept for any function? I'm going to copy the function here. How do we find the y-intercept? Always, we determine f of
0.
Excellent. How much is 0 plus 1?
1.
How much is 2 to the first power? 2. 2 times negative 1.
-2.
Negative 2 plus 4.
6. Or sorry.
But that's okay. I thought for a second myself. So 0, 2. And that is the y-intercept. Okay. So coming back, we determined them algebraically. We have them now. But now I want to graph the function. And I will graph everything. When I graph 2 to the x, I know it's an increasing function. And it has to cross at 0, 1. This is carved in stone. The pure exponential function, 2 to the x, it's an increasing function on all its domain, and it crosses the y-axis at 0, 1. Now we have to shift this graph 1 to the left. So this point moves 1 to the left, meaning it will be at -1, 1. So I shift the graph. So this is 2 to x plus 1. And this point now is -1, 1. This one. Next, you told me to reflect the graph with respect to the x-axis. I completely agree. So now this point gets reflected here. It will be at -1, -1. And the graph is this. So this is the graph of -2 to x plus 1. I haven't talked about the horizontal asymptote because all these 3 graphs had the same horizontal asymptote at -∞. But now the final step asked me to move this graph up 4. So this graph moves up 4. I cannot move it up before I move its horizontal asymptote. All these 3 had the horizontal asymptote y equals 0. Where is the horizontal asymptote of the last graph, of the original function? Not broken down in small pieces. So if I move this graph up 4, I have to move the horizontal asymptote as well up 4. So initially it was 0. It has to go up to 4. 1, 2, 3, 4. So this is y equals 4 horizontal asymptote of the new graph. Now, because I already have the x and y intercepts, I am going to pay attention and put them correctly. So the y-intercept is 0, 2, and the x-intercept is 1, 0. And here's the graph. And of course, this point now moves at -1, 3. 1, 2, 3, 4. The entire graph moves up 4. Can anyone give us the range of this function? I'm going to do this to make sure that you understand which one is the final graph. So this is the final. -2 raised to x plus 1 and plus 4. Can anyone give us the range of this function? See what happened? Go ahead.
Negative infinity to 4.
Very good. See what happens from the pure exponential function? If I throw in some transformations, the whole thing changes, not the domain though. But the range changes, even a base of 2. If I throw in some transformations, I can make it decreasing. And we know that this is the pure exponential function with a base greater than 1. It's always increasing. But if you throw in some transformations, the whole thing changes. Again, not the domain. Okay. There are a lot of applications of this function. A lot of applications. So I'm looking on page. They show a lot of transformations and graphs to read from graphs. I just would like to look at an application. On page 475, I would like to look at accumulated value of an investment. So problems 53 through 56. So before we look into this, I'm going to say that there are two special, if you want, exponential functions. One has base 10, and this is called common exponential function. And the other one with a base e, and this is the natural exponential function. They are so special that they have a special key dedicated to them in the graphing calculator. So let's look at the calculators for a minute. Here it is. See right here in the back on the base of the calculator where it says log, but next to it it's in blue or yellow depending on your calculator, and it will be activated with the second key, which is 10 to the x. And the next one down from 10 to the x is e to the x. It's where the key is ln, and in the background is e to the x, which will be activated with the second key. The common exponential function and natural exponential function. Okay. Because both of them have base greater than 1, their graph will look like this. The higher the base, the closer to the y-axis. So if this is e to the x, this will be 10 to the x. Closer. You can also put them in the graphing calculator. Of course, you notice the pure exponential function has to cross at 0, 1. For sure, forever, if it's pure. No transformations, I mean, by pure. Okay, so one application that I would like to look at is what is called compounded interest. This is a fancy word for really saying recalculated. That's what it means, compounded interest. The interest can be compounded n times per year, or it can be compounded continuously, which means every second. Of course, the formulas are different. Of course, you will not have to memorize them. They will be given to you. So here's the formula for n times per year, compounded interest. I will explain each piece, but I'm going to write it here so you have it. P1 plus r over n raised to n times t. And this one is a equals p e to r times t. And now what's with all these letters? That you have to remember. A is the accumulated value of an investment. For example, we put in an account, we put $1,000 today. We want to go back and take it out 10 years later. That will be the accumulated value. P is the principal amount. Whatever we deposit today. We deposit today $1,000. In 10 years, let's say we have $3,000. That's the accumulated value, and P is the principal. Lowercase r is the annual interest rate. Lowercase n is the number of times we recalculate, we compound the interest. N, number of times we compound the interest per year. And finally, T, time in years. So now feel free to choose any problem you like between 53 and 56 to illustrate this. And this is the same. E is the base of the natural exponential function right here as I showed it. R the same, T the same. So if you want to choose, if not, I will.